So multicollinearity. This occurs when the independent variables have are correlated, especially when they're strongly correlated. Okay, instead of being independent of each other. So this is the book will tell you that this is not a problem because the coefficient estimates are unbiased. Now, in my experience, a lot of times correlation among variables will create some weird things going on with the coefficient estimates. And I think we saw that in the last video when we looked at the effect of bedrooms on price. Okay, as you'll see, if I'm ever able to crank up SPSS again, I never find a satisfactory solution for why bedrooms might be a problematic variable. But I'm pretty sure it's because of some weird correlation among the variables. So I'm not so sure that multicollinearity is not a problem in terms of coefficient estimates. But typically, the problem is what's called variance inflation. The standard errors will be larger than they really are when predictor variables are correlated with each other. What this does is it makes the t-statistics too small and increases the confidence intervals on the coefficients. And it is difficult to separately to determine the separate contribution of each predictor. It's difficult to interpret what those contributions are. So multicollinearity is a common problem in multiple regression analysis. So detecting collinearity or detecting multicollinear and collinearity are two different things. Collinearity is when you are just checking to see if any two predictors are correlated. Okay, and what you do in that situation is estimate the correlation between those two variables, or between all of the variables, which is known as the correlation matrix. And if the correlation between those variables is high, in a quote, some quotes, then if the correlation is high and one or both of the variables have low t-statistics, then collinearity may exist. Okay, an extreme situation is if two variables are positively correlated with the independent variable, but one has a negative slope in the multiple regression. Okay, so Klein's rule. So this says we should worry about the stability of the regression coefficient estimates when the pairwise correlation, r, lowercase r, that we defined early in chapter 12, or we reviewed early in chapter 12, exceeds or is greater than multiple correlation coefficient. And that is r, capital R, which is the square root of the r squared variable. Okay, we've solved the problem. Another thing that you want to consider is coefficient stability. So we have two variables that are strongly correlated, and so what we want to do next is try dropping one of the predictors from the regression to see what happens to the other coefficients. So in that situation, we drop the number of bathrooms from the model to see if that's going to affect the coefficient on the square foot. If the square foot variable doesn't change much, then we can say that collinearity is not much of a concern between the number of bathrooms and the square footage. But if it does change one or more of the coefficients in the model, then collinearity may be causing instability. Let's say you are interested in detecting multicollinearity. Okay, the problem with the correlation matrix is that it only shows correlations between any two predictors. It might be that there is correlation between more than two predictors. Okay, so multicollinearity. Okay, so one way of detecting multicollinearity is with what's known as the variance inflation factor. Okay, and the variance inflation factor, the statistic, is equal to, for any predictor J, you have a unique variance inflation factor for each predictor in your regression model. Okay, the variance inflation factor is equal to 1 divided by 1 minus the r squared sub j, where the r squared sub j is the coefficient of determination, the r squared value, when predictor j is regressed against all other predictors. We have a variance inflation factor of 1.85 estimated. And here I'm telling you that this can be done quickly using SPSS. But here is an interpretation of what those values might be. Okay, so for the r sub j squared going from 0 to almost 1, the variance inflation factor is going to range from 1, okay, 1 divided by 1 minus 0 is equal to 1. And here's the number close to what we just found, 1 divided by 1 minus 0.56, and that gave us 1.85. And so we're close to 2, so we might say that there's mild variance inflation as a result of the multicollinearity between bathroom square foot and lot size. Okay, as you go from 0.5 to 0.9, the textbook tells us that we go from 2 to 10 and we have strong variance inflation. And let's just stop there because we're not going to find many cross-sectional data sets with an r squared amongst these variables of 0.99. But that leaves a pretty big range between 2 and 10 where we might think of problems where we have multicollinearity. Okay, and once SPSS cranks up, we will look and see how SPSS can quickly estimate the variance inflation factor. Okay, and let's wrap up chapter 13. Let me just remind you that the other regression topics that we covered in chapter 12, heteroscedasticity, unusual observations, leverage, outliers, and some other things that we quickly covered. All of those apply to multiple regression. Detection of these problems is the same, and the solutions, or the potential solutions, tend to be the same.